Yeah, hello everyone. Welcome to the session 9 of Theory of Computation or Formal Languages and Automata Theory. So in this session, we are going to discuss about the minimization of the DFA. Okay, so how do we reduce the size of a given DFA? So that concept here we are calling it as minimization of DFA. So in this session, we are going to discuss the algorithm for the minimization of the DFA, and we will solve some of the problems related to that minimization problem. Okay, so in the previous session, we discussed about the equivalence of NFA and DFA, and we discussed the subset construction algorithm that we use for converting the given NFA into the DFA. Okay, so these are the problems which we have solved in the previous session, where we converted the given NFA into the DFA. Okay, so we used the two methods for that conversion of NFA into the DFA. Okay, so, whenever we convert a NFA into the DFA, the number of states in the DFA will get increased, right? So, we have seen that if NFA is having n state, and if we convert it into an equivalent DFA, it may have 2 power n states. Okay, so at most 2 power n states are possible in the equivalent DFA, right? So, uh, uh, we need to minimize the DFA. Okay, so it becomes mandatory to minimize the size of the DFA. So how do we reduce the size of the DFA? Okay, so in order to reduce the size of the DFA, we have to remove unnecessary states from the DFA. Okay, so one of the possible ways for minimizing the DFA is removing of unnecessary states. Okay, so the question is that how do we find out the unnecessary states from the DFA so that we can eliminate it to make it as minimized DFA. Okay, so that is the question. So basically, unnecessary state means whose removal from the DFA will not change the language acceptance of the DFA. Right. So, for example, we are having a DFA which accepts some set of strings ending with A. Right. So, unnecessary states removal means you have to identify the states in which the removal of those states will not affect the language acceptance of the DFA, right? So the language which is accepted by the DFA must not change. Okay, so the removal of those states should not influence the language accepted by the DFA. So such states can be eliminated from the DFA. Okay, so here if you observe the first point in this one, it is possible to have it is possible to have more than one DFS that accepts the same language. Okay, so obviously it is very much possible to have the multiple DFS that accepts the same language, of course. But among these DFS, it is necessary to find the smallest DFA. Okay, so what is the smallest DFA? Say DFA which is having the minimum number of states. Okay, so let me give one example. So we have designed a DFA1. Okay, so we have designed a DFA1 which accepts the language L, right? Similarly, second person has designed a DFA D2 which accepts the same language, right? So here these two DFAs are accepting the same language, right? So if we ask a question here, among these two DFAs, which DFA is the efficient one? Right. So if I ask a question here, among these two DFAs, which DFA is the efficient one? So the answer is the DFA which is having the less number of states and it is accepting the language L is the efficient one, right? So let me consider DFA D1 is having some 3 states, it is accepting L, and DFA D2 is having 2 states, it is accepting the language L, right? So among these two, the DFA D2 is the efficient one. Why? Because it is having the less number of states. So whenever the DFA is having less number of states, it is going to occupy less amount of memory. Okay, so it requires less computational resources. So the DFA which is having less number of states is considered as the efficient one. Why? Because since the states are less, it is going to require less computational resources. Okay, so what will happen usually when we convert the NFA into the DFA, the number of states will get increased, right? So whenever you convert NFA into the DFA, it is mandatory to minimize the DFA, right? So what will happen if you minimize the DFA? The number of states will get reduced. Okay, so this we call it as D of M is minimized DFA. Okay, so NFA to DFA, then we have to minimize the DFA. So this is one of the reasons why we are going to discuss about the concept of minimization of the DFA. Okay. So how do we reduce the size of the DFA? Okay. So to reduce the size of the DFA, we have to eliminate the unnecessary states. Okay. So next thing we will discuss how to eliminate these unnecessary states. Okay. And what are the unnecessary states? So first thing, we have to identify the unreachable states. The first thing is that we have to identify the unreachable or inaccessible state. So what is this unreachable or inaccessible state? A state that cannot be reached from the start state is called as the unreachable state, right? So a state which cannot be reached from the start state is called as a unreachable state. So in the DFA, one of the most important point is that every state must be reachable from the start state, right? So if any state is not reachable from the start state, then it is considered as unreachable state or inaccessible state. So such states must be eliminated from the DFA. Okay. So whenever you have given a problem with this minimization of the DFA, what you need to do is that first you need to identify the unreachable or inaccessible states, right? If there are unreachable or inaccessible states in the given problem, you need to eliminate it first. Okay. Next one, identifying the indistinguishable or equivalent states. Okay, so we have to identify the equivalent states in the DFA and merge them, and the merging of those states will not change the language accepted by the DFA. Okay, so the states are said to be indistinguishable if their merger does not change the language accepted by the DFA, right? So we need to find out the equivalent states in the DFA. So let me say if we are having the two equivalent states, that means Q0 and Q1, those two equivalent states can be merged together, right? So what will happen? In the given problem, these two are the separate states, right? So if you find these two states are equivalent, then what you will do, you merge these two states into the single state. Okay, so this is the second point that you need to consider. Okay, so minimization of the DFA requires the elimination of two states. One is the unreachable states and next one is the indistinguishable states. Okay, so what we are doing, we are eliminating the equivalent states. How we are eliminating? We are merging the equivalent state as a one state. Okay, so that is the point here. Okay, then the next question is that when we can say that the states are indistinguishable or equivalent states. So just understand the principle here. The two states P and Q of a DFA are called indistinguishable if and only if delta of p comma w, that means p is some state and w is some string, if processing the string w from p, if you get a final state, then it implies that processing w from state q will also leads to the final state, right? So try to understand this one. Delta of p comma w belongs to the final state, then it implies that delta of q comma w also gives the final state, right? This is the one of the conditions to prove that the states are indistinguishable or equivalent. Otherwise, if delta of p comma w does not belongs to the final state, it implies that delta of q comma w also does not belongs to the final state. Okay, so whenever you perform the transition from p on w, if you get a final state, then definitely on processing w from q should also give the final state. Okay, so this is one of the conditions. Or on processing w from p, if you don't get a final state, it implies that processing w from q also doesn't give the final state, right? So if any of these conditions are satisfied, then the states are called indistinguishable or equivalent states. So in this case, you can merge the states P and Q as a single state, right? So in the given DFA, the P and Q will be the separate states, right? So whenever these any of these properties holds good, then you can merge these two states as a single state in the minimized DFA. Okay, I hope the point is clear now. Next, so when we can say that the two states are distinguishable, I mean the two states are separable, that means we cannot merge them. So the two states P and Q of DFA are called distinguishable, that means they will be the separate one, we cannot merge them if delta of P comma W gives the final state, that means delta of P comma W belongs to the final state, and delta of Q comma W does not belongs to the final state, then the P and Q are distinguishable. That means you cannot merge them. Why? Because one on processing W from P, it is giving the final state, but on processing W from Q, it is not giving the final state. So we can say that the states P and Q are distinguishable. That means we cannot merge them. They must be the separate states in the minimized DFA. Okay. Or if delta of P comma W does not belongs to the final state and delta of Q comma W does not belongs to the final state, then again the states P and Q are distinguishable. Again we cannot merge it. Okay. So these are the basic points or the basic principles which are required for minimization of the DFA. Okay. So this is the algorithm here which we are using for constructing the minimized DFA. Okay. So here just try to understand. So just I am going to give a brief overview about this algorithm. So when we solve a problem, then you can able to understand this algorithm in clear. So first thing, initially construct zero equivalent class. So here, see here, I have written phi naught. Okay, so phi naught. Phi naught is nothing but it is a set of final states and non-final states. So let me consider here we are having Q1. So Q1 is nothing but some set of states and Q2 is some other set of states. So we are having two set of states. Okay, and 0. So here if you observe the subscript is 0. So we could say here we are having the first partition set. So here pi naught is the partition set 0. Okay, so pi naught is the partition set 0. Okay, so what it means, we have divided or partitioned the states of DFA into two sets. Okay, one is the set of final states and one is the set of non-final states. So this is the first partition set that we write in the algorithm, right? So where q1 power 0 is the set of final states, right? So the first set we are writing here is the set of final state, and next q2 power 0 is the set of non-final states. So first thing, whenever a problem is given, first thing is that you have to generate the pi naught, right? So what is this pi naught? It is nothing but set of two set of states, right? What are those two sets? One is the set of final states, okay? One is the set of final states, and next one is the set of non-final states, okay? So two states we are going to have in this, right? So we have to first divide the states into these two sets. That means we are partitioning the sets. Okay. Next, so what we will do is that we will construct pi k. That means pi k plus 1. Pi k plus 1 from pi k. That means whatever the pi value that we are considering, that means whatever the pi set, current pi set that we are considering, we are calling it as a pi k. So whatever the current partition set that you are considering, it is considered as a pi k, right? And whatever the newer partition set that you are generating, it is called as pi k plus 1. So here if you consider here, we have taken the initially the partition set as pi naught, right? So from this pi naught we are going to generate the partition set pi 1, right? Partition set pi 1. So how do we generate this pi 1 from pi 0? That means how do we generate pi k plus 1, that is this one, pi k plus 1 from the current partition set pi k. Okay, so what you need to do is that you have to take each state set from pi k, okay, in this example pi naught, and you have to identify the distinguishable and indistinguishable states. Okay, so you have to identify the distinguishable or non-distinguishable states. Okay, so if the states are distinguishable, then you have to partition that state set. If the states are not distinguishable or equivalent, then you have to keep the set as it is. Okay, so this is how we can generate the newer partition set from the existing partition set. Okay, so this process, that means from pi naught we generate pi 1, from pi 1 we generate pi 2, from pi 2 we generate pi 3, so on, right? So this process continues until the two pi values becomes equal, right? So this process continues until the previous pi value and the newly generated pi values are equal, right? So this is how the algorithm works. Okay, so we will do one example and then we will come back to this algorithm once, so that you will get the clear picture of this algorithm. Okay, so try to practice on a paper if possible. So construct the minimum DFA for the given DFA. So here the problem is we have to construct the minimum DFA, that means you have to minimize the DFA for the given DFA. Okay, so this is the given DFA and this is the transition table that we are having. Okay, so right, first thing, this is the DFA, right? So we have to check and we have to apply the algorithm to understand whether it can be minimized or not. Okay, first thing what we have to do, as I mentioned, that we have to identify the pi naught, right? What is pi naught? It is consisting of two state sets. One is the set of final states and one is the set of non-final states. Okay, so non-final states, set of final states and set of non-final states, right? So in the given DFA, what is the final state? What are the final states we are having? So we are having only one final state, q4. So q1 power 0 will become set of q4. Okay, and next what are the remaining non-final states? So that must be the value of q2 power 0. So q2 power 0 is equal to set of non-final states. So very simple. What we have done is that we have taken the pi naught and we have separated the states in the DFA into the two categories. The category 1 or the set 1 is nothing but set of final states, and next the set of non-final states, right? So that is the pi naught, right? So from this pi naught we have to construct the pi 1. Okay, so how do we construct the pi 1? So pi 1, the construction of pi 1 means we are checking the states in the pi naught for the property of distinguishable or non-distinguishable, right? So if the states are distinguishable, what we can do is that we can keep them as a single set. If the states are if the states are distinguishable, we have to divide the state set. If they are non-distinguishable, we have to keep them in as a single set. Okay, so that we have to identify. So how do we identify? We have to consider the each state and we have to compare it with the other one, right? So step 2 or B is construct pi 1 from pi naught. Okay, construct pi 1 from pi naught, right? So we have to check the equivalence of the states. So here you could see we are having the two state sets. One is the q4 and another one is the q0, q1, q2, q3, right? So what you have to do is that we have to take each set and we have to check the states for property of distinguishable or undistinguishable, right? Since in q1 power 0 we are having only one state, we cannot compare it with the other, so the set remains same, right? So we cannot able to compare it with the other states because this set is having only one state only. So we cannot able to compare with the other state because it is having single state. So this set will remain as it is, right? So here you could see q1 power 0 cannot be divided as it has only one state. Okay. Next what we have to do is that we have to consider this state, this set. In this set, what you have to do is that you have to check the states for the property of distinguishable or indistinguishable. That means you have to compare the states for whether they are distinguishable or not, right? So compare q0 q1, compare q0 q2, compare q0 q3, likewise. Okay, so we have to take each pair of states from the set, and we have to check for distinguishable or indistinguishable property, right? So here you could see q2 power 0 has 4 states. We need to identify whether they are one equivalent or not. Okay, so one equivalent means whether they are equivalent in pi 1 or not. Okay, that is the meaning, whether they are equivalent in pi 1 or not. So that is the meaning, whether they are one equivalent means they are equivalent in pi 1 or not. Okay, so first thing, compare q0 and q1, right? So first take the two states, pair of states q0 q1, and compare them, right? So how do we compare? Perform the delta transition, right? Delta of q naught comma 0. So first check the transition from q naught on 0 where it is going, and then similarly check for transition from q1 on 0 where it is going. So here you could see delta of q naught on 0, it is going to q1. Delta of q1 on 0, it is going to q2. Okay, so here q1 and q2 are not final states. Okay, so here here it is satisfying the property that delta of p comma w is not giving the final state. It implies that delta of q comma w is also not giving the final state. Okay, so for this input these two states are equivalent, right? So we have to check for the other input, right? So delta of q naught comma 1 is equal to q2. That is, it does not belongs to the final state, right? And delta of q1 comma 1 is giving the state q4, which is the final state, right? So here you could see delta of p comma w is giving non-final state, whereas delta of q comma w is giving the final state. So this property is making these two states are what? These two states are distinguishable. That means these two states are different, right? Because one is going to the final state and one is not going to the final state, right? So what we will do is that these two states will be partitioned, right? So what will happen? Q naught is not one equivalent to q1, right? So q naught will not be present in the q1 set. Okay, so that is the meaning. So q naught q1 we cannot merge it, right? Then what we have to do is that compare q naught and q2 on input 0 and 1, right? So next we are comparing q naught with q2, right? So q naught with q2. So just compare it. Delta of q naught on 0 where it is going q1, then delta of q2 on 0 where it is going q3, right? So it is satisfying the property that delta of p on w, it is giving non-final state, and similarly delta of q comma w, it is also not giving the final state, right? So they are seems to be one equivalent for the input 0, right? So next we have to check for the input 1. So delta of q0 comma 1 is equal to q2. Delta of q2 comma 1 is equal to q2, right? So again, delta of q0 on 1 is not giving the final state, so it does not belongs to the final state. And same delta q2 comma 1 is also not giving the final state, right? So here these two states are equivalent, right? So q naught and q2, they should be kept in the same set, right? So q naught and q2 must be the in the same set, right? Next compare q naught and q3 on the input 0 comma 1. Okay, next delta of q naught on 0 q1, delta of q3 on 0, it is q2, right? So both are not giving the final state. Very good. Next delta of q naught on 1, it is not giving the final state. Delta of q3 on 1, it is giving the final state. So one is not giving the final state and another one is giving the final state. So q naught is not one equivalent to q3. That means q naught must not be present in the q3 set. Okay, so q naught and q3 should not be present in same set, right? So they must be separable, right? So by finding out these things, we can able to understand here q naught and q2 are indistinguishable. That means they must be kept together as a single set, right? Remaining states we have to see here. So now pi 1 is equal to q1 power 1, q2 power 1 and q3 power 1. What happened? The state set has increased, right? So why it has increased? The first one set of final state, so it remains same q4. The next one, what happened here? By checking this property, we found that q1 and q2 are equivalent. So they must be kept in a separate state. So that's why in q2 power 1 we got set of q0 comma q2 because they are indistinguishable. They are equivalent, right? And next the remaining q3 we are having q1 comma q3. Okay. So q0 q0 q1 q2 q3 among these state set we identified q0 q2 must be in a single set. Why? Because they are equivalent and they must be separated from q1 and q3. So that is the reason we got three states set in pi 1. Okay. Now compare this pi 1 value with pi naught. So are they equal? No, they are not equal. In pi naught we are having only two state set, but in pi 1 we are having three state set and they are not identical, right? So now what you have to do is that you have to construct pi 2 from pi 1. Okay. So next we have to compute pi 2. So how do we compute pi 2? Take each state set and check for the equivalent states, right? So q1 power 1 we cannot partition it. Why? Because it is having only one state. Okay, next q2 power 1, take this state set q2 power 1 and check for the property of distinguishable or indistinguishable, right? So what are the states in q2 power 1? q0 q2. So check for that input 0 and 1 and check whether they are equivalent or not. Delta of q0 on 0 where it is going q1, delta of q2 on 0 where it is going q3. Okay, so both are, so what is happening here? So both are giving non-final states here. Okay, non-final state. Next, delta of q naught comma 1 q2, delta of q2 comma 1 q2, non-final states, right? So here observe. So here when you perform the transition function, if you get a non-final state, those non-final states must be the members of the same set, right? So here you could see delta of q naught on 1 means q1, it is non-final state, right? So it is a member of state set q3, right? Similarly, delta of q2 comma 0, what you got? q3. So it is also the member of same set q3, right? So if you have got something like q2, something like q2, you could directly say that they are indistinguishable. Why? Because delta of q0 on 0, it is giving non-final state, which is the member of q3, and delta of q2 on 0, it is giving q2, which is the member of q2, right? So we are getting the non-final state, those belongs to the different state set. So in this case we have to mark these two states q0 and q2 as distinguishable. This is the most important property. Okay, so that is the thing here. Next, check it. Delta of q naught on 1. What you got? q2. So q2 is the member of non-final state, which is a member of q2 power 1. Next, delta of q2 on 1. We again got q2, which is the member of q2 power 1. So these two are the member of the same set. These two are the members of same set. So based on this, we can say that q naught and q2 are two equivalent. They are two equivalent, right? So two equivalent means they must be in the same set in pi 2. Okay, that is the meaning. So they are two equivalent. Done. Next, what we need to do is that we have to check whether q1 and q3 are equivalent or not, right? So you have to take q3 power 1. Yes, you have to take q3 power 1 and we have to check delta of q1 on 0. What you got? q2. Delta of q3 on 0, q2. So resultant state belongs to q2 power 1. So both are the members of the same set. Okay. Next, check for 1. Delta of q1 on 1, q for. Delta of q3 on 1, q for. So both are giving the final state. Yes. So obviously we can say that q2 and q3 are two equivalent. That means we cannot partition. In pi 2, they must be in the same set, right? So what is the pi 2 value that we are having? q1 square, q2 square and q3 square. That means q1 power 2 comma q2 power 2 and q3 power 3. So we are having three states. Okay, the first state set, sorry, we are having three sets. The first set is having the final state, second set q2 q0 comma q2, and third set q1 comma q3. Okay, now so if you observe, pi 2 and pi 1 values are same. Pi 2 and pi 1 values are same. So here this partitioning method will end here, right? So this process ends here. So now what are the possible states in the DFA means Q4 is the one state, okay? Q4 is the one state. Next one, Q0, Q2. So Q0, Q2 we have written as a single set, na? So these two states must be merged together. So Q0, Q2 will be the one state. Okay, they are not separate state, they are one state. Q4 is the one state, Q0, Q2 is one state, and Q1, Q3 is one state. So Q1, Q3 is one state. Okay, Q1, Q3 is one state. So totally three states, right? So instead of Q0, Q2 together, we can also write Q0 2, that is Q02. You could also write Q02. You may also write Q13. Okay, Q13. So anyways, both are the possible ways for the representation of merging states. Okay, so any of the way you can use. So here you could say Q4 comma Q0 Q2 Q1 Q3. So we are having three states, right? Then specify the transition. Okay, so Q0 Q2 Q1 Q3 and Q4. Then specify the transition, right? So those transition you specify from the given DFA itself. Okay, so in the DFA, so you could see here. So Q naught on 0 Q1, Q naught on 1 Q2. So Q naught on 0 Q1. So where we are having the Q1 as a member, make a transition towards that. So Q naught on 0, we are having the transition towards Q1 in the given problem. So in the resultant DFA, wherever you are having the Q1 as a member, then you have to make a transition towards that state. So Q naught on 0 means Q1. Q1 on 1, Q2. So Q2 is the member here. So we are going to get a self transition, right? So like this, you have to specify the transitions by considering the given DFA. Okay, right. So if you observe here this algorithm, so what we are doing here is now the algorithm is clear for you, I think, right? So what we are doing, we are constructing pi k plus 1 from the pi k by using the partitioning approach, right? So let q1 k. So we are selecting one of the state set from pi k, and we are checking whether the two states q1 and q2 are equivalent or not, right? So so this process we will repeat until pi n is equal to pi n plus 1, right? Or pi k is equal to pi k plus 1. So this process is repeated until this property, until this condition is satisfied. Okay. Next, construct the minimum state DFA with states obtained by equivalent class, okay, of pi n. So whatever the state set that we get in the final pi n value, pi n set, by using those states we are going to construct the minimum DFA. Okay. So this is the overall process of partitioning method that we use for constructing the minimum DFA. Okay, so just try to reduce the DFA. So just try to solve this problem here. So it is a simple problem, right? So first thing, uh, we have to check for unreachable states. So we are not having any unreachable states. So in every problem, you have to check for this property, right? So you have to check whether there are any unreachable states or not, right? So what are unreachable states? The states which are not reachable from the starting state, right? So those are unreachable states. So property one is that you have to check for unreachable states. So let me say we are having the state something like P, Q, R. Okay. So let me consider P is the starting state. P on 0, it is going to Q. Q on 0, it is going to P. Okay, and R on 0, it is going to P. Okay, so here you could see in this diagram One state is unreachable. What is that state? Can you figure out? So what is unreachable state? A state that cannot be reachable from the start state, right? So which state is not reachable from start state P? Of course R, right? Why? Because we are not having a path from start state to R, right? So this state can be eliminated, right? So this is the first step called as removing the unreachable states, right? So in the given DFA, you have to find out whether there are unreachable states or not, right? Since there are no unreachable state, you can directly go for pi naught construction. So what is pi naught? Dividing the state set into the partitions, right? So that consisting of set of final states and non-final state, right? So what are the final states here? Q and R. So write them as a one set. What are the non-final state? P is the non-final state, right? So write it as a single set, right? Next, construct pi 1, right? So in pi 1, what you need to do is that you have to take each set and we have to compare the states in that set whether they are distinguishable or not, right? So here Q and R we are having, so compare those. So the delta of Q naught comma 0, it is giving P. Delta of R is equal to 0, it is giving P. Both are non-final state and this is the member of same set only. So both non-final states are member of same set. So this property is satisfied. So they are indistinguishable at this particular input, right? So we have to check for 1. So delta of Q comma 1 is equal to R and delta of R comma 1 is equal to Q. So both are giving the final state and both are the member of same set, right? So here you could say Q and R are one equivalent. That means they must be kept together as a single set in pi 1. Okay. Next, you have to take next set. What is the next set? P. So since we cannot have any states to compare, so that set will remain as it is. Okay. So consider P, since it has only one set, we cannot compare. So finally, what is the pi value? Q comma R in one set, comma P in another set. So if you check, pi 1 and pi naught are same. So partition method ends here and the states are Q R as a single state and P as a another state. So two states. So this is the minimum DFA. Okay. So in this fashion we can construct the minimum DFA for any given problem. Okay. So I hope the concept is clear. If you get any doubts, just feel free to get in touch with me. Okay, and I will answer those queries in the next session. Okay, thank you for watching this session.